In this video, we're going to talk about batching and separating entities. And specifically, we're going to talk about the combiner and the separator um, object definitions that we can use for batching and unbatching. And we will also talk about the batch and unbatch steps that we can use in Simio processes and add-on processes. So let's start with the first model, that is a palletizer model. And in this model, we're considering a system that consists of three main steps. So we have individual parts that arrive into the system, and they're first put on a pallet. Once they're put on the pallet, the pallet and the parts move to the next station, which is a processing station. And here we have a batch processing station. So we process parts that are on each pallet. And the processing time of a batch depends on the number of parts that are in that batch. Once the batches are processed, then we have the depalletizer station where individual parts leave the system, but our pallets circulate in the system. So we have a fixed number of pallets that circulate in the system. Parts are put on the pallets, move through the system, and once they're finished, parts leave the system, but pallets go back to the palletizer station. So again, the idea is that we have a fixed number of pallets, and each pallet and the pallets have a certain capacity. And the decisions that we're trying to make using this model is how many pallets do we need, and what is an appropriate capacity for each pallet. So in terms of the arrival process, we have an inter-arrival time that is uniformly distributed between 0.75 and 1.25 minutes. So the average inter-arrival time for individual parts is 1 minute. As I mentioned, we have a batch processing station here, and the processing time for each part is exponentially distributed with mean 0.9 minutes. So we have a processing rate of 1.11 parts per minute. But again, since we have this batch processing operation here, the processing time of the batch depends on the number of parts that are in the batch. And since we're adding multiple exponentially distributed processing times, the total time processing time for the batch is going to follow an Erlang probability distribution. The palletizer and depalletizer processing times are between 10 and 20 seconds and are uniformly distributed. So it takes between 10 to 20 seconds to put parts on the pallet, and then before the parts leave the system, it takes about 10 to 20 seconds to take the parts off the pallet. The time that it takes for the pallets to return to the palletizer station is also random, and it's assumed to be triangularly distributed with a minimum of 5 minutes, a maximum of 25 minutes, and a mode of 15 minutes. And again, the decisions that we're trying to make in this model is the number of pallets. And again, remember that we have a fixed number of pallets that circulate in the system. And we also want to find the pallet capacity. So we would like to know whether we need pallets that have a capacity of 2 parts or 4 parts or 6 parts. And we also have some requirements for the performance of our system. We would like to have a minimum throughput in terms of parts per hour that leave the system of 55 parts per hour. And we would like to keep the average time in system less than 1 hour. So let's take a look at the Simio model of this system. In this model, we have two types of model entities. We have pallets and we have parts. So we use a different symbol to represent our pallets. And if I can select the Q of the pallet here, you can see that we're using the point alignment for to indicate where the parts will be put on the pallet. And we have two source objects. The first source, as you can see, generates pallets, and the inter-arrival time is set to 0, and the maximum arrivals that occur is set to 1. But the number of entities that are created in that single arrival event is set as a reference property that we call num_pallets. So if I go to my model definitions, I have a set of reference properties defined. One of them is the number of pallets that I have in my system, and it has a default value of 5. So what happens is when I initialize the model, this source will generate 5 pallets at time 0, and then it's not going to generate any more pallets during the run. The second source, however, generates parts, and we have the expression for our inter-arrival time for parts as specified by the problem description. So pallets and parts are combined using a combiner object. So pallets enter the combiner as parent objects, and parts are members, and then based on the number of parts in each pallet or in each batch, parts and pallets are combined using this combiner station. So when you look at the properties of the combiner object, you will see that we have again set another reference property to represent the batch size, which we call pallet capacity. So again, if I go to my model definitions properties, I have the pallet capacity defaulted to 4. So now currently my batch size is 4. I have 4 parts on each pallet. So pallets and parts then move to the server, and as we talked about, since we're adding multiple exponentially distributed processing times, the processing time for the batch is going to follow an Erlang distribution. So we're using the Erlang distribution for the processing time of the batch. And finally, once the batches are processed on the server, the batch then moves to the separator, where the pallet and the members, which are parts, are separated from each other. The pallets go from the parent output of the separator back to the combiner. Remember that we have a fixed number of pallets that circulate in the model. And then we have the parts that go to the sink. So let us run the model and see what happens. So at time 0, I generate 5 pallets. And then as soon as I have 4 entities, I form a batch. The batches then move to the server. They're processed on the server. In the separator, the pallet is separated from the parts. The pallets go back to the combiner, and the parts leave the system through the sink. We're using a status label that is attached to our sink 1. So if I move sink 1, you will see that the status label also moves with it. And this status label, the expression that it shows or evaluates, is input buffer dot number entered. So this value 36 shows me 36 entities entered the input buffer of the sink. So when you watch this model run, you will see that we will have a queue built up here at the member node of the combiner, while these parts could have been moved to the server. And as you can see in this case, the server is idle, but we have this long line of parts that are waiting to be combined with the pallets. So this shows that having more pallets or a higher capacity for the pallets can help us process parts faster. So now that we know the number of pallets and the pallet capacity can influence the performance of our system and our throughput, let's go ahead and change these two parameters of the model and run the model again and see what happens. So I'm going to this time have 8 pallets circulating in my system, each with a capacity of 6. So now I expect to be able to move parts faster from the combiner to the server, and hopefully see fewer cases where the server is idle but I have parts that are waiting to be transported to the server. So let's run the model and see what happens. And again, as you can see, now initially when the model starts, we generate 8 pallets, and each pallet has a capacity of 6 now. We're going to let the model run for a while. Let me increase the run speed a little bit. Let's change it to 10. And hopefully we won't see that much idle time for our server object, since we increase the number of pallets and the pallet capacity. So in order to make a decision on an appropriate number of pallets and the pallet capacity, we ran an experiment, and as we all know, since we're using reference properties for these two parameters, number of pallets and pallet capacity, and the two reference properties also appear as controls in our experiment, allowing us to define multiple parameter configurations or multiple scenarios all in one experiment. So in this experiment, we try different number of pallets and different pallet capacities. So we change the number of pallets from 5 to 7 and 8 pallets, and also the pallet capacity from 2 to 6 parts per pallet. So we ran 10 replications of each scenario. When you look at the properties of our experiment, we have set the primary response of our experiment to be the throughput, and our response for throughput is defined as the number of parts that leave the system divided by the total simulation time that is stored in time now at the end of the simulation run. We also have defined the response for the average time in system for all of the parts that leave the system. And we get the average time in system from the sync object, so sync1.timeinSystem.average, and we know that the unit type is time, and we have this upper bound of 1 hour for the time in system as specified by the problem description. We've also defined this response for the average number in system for parts. One thing that I forgot to mention that is we also have this lower bound on our throughput that is set to 55. We want to have a throughput of 55 parts per hour, and our objective is to maximize our throughput. And since we have set the requirements for our throughput and time in system, you will see that Simio shows the scenarios that violate our requirements by this red color. But we have 5 scenarios, scenario 3, scenarios 5, 6, 8, and 9, that do not violate our requirements and seem to have a very close throughput values, although their average time in system seem to be a little bit different. So let's just get rid of the scenarios that clearly violate our requirements. So I'm just going to deselect these scenarios and just focus on these 5 scenarios that are potentially good. So I'm going to look at the smart plots of the throughput, Let me actually go ahead and sort my uh, scenarios in a descending order of the throughput. And now I'm going to look at the smart plot for the throughput. And as you can see, I have sorted my average throughput values in a descending order. But since we have these wide confidence intervals, it's really hard to determine which one is the best among these five in terms of the throughput. So this one has the highest average, but the confidence interval goes down to 59.84. So the average for this one can be very well down here, while the average for this one can be up here. So it's based on the number of replications I have right now. Since I have a high sampling error, it's really hard to statistically establish which one is the best among these five scenarios. Similarly, when we look at the timing system, we can see that for some of them we have overlapping confidence interval, and again the same problem that due to high sampling error we cannot statistically choose the best among these five scenarios. So what I'm going to do is use the subset selection add-in in Simio that essentially performs statistical tests and divides my set of scenarios into two sets, a potentially good and or potentially best and a bad set. So if I actually use the subset selection, you will see that in terms of the throughput, my scenarios are divided into two sets. So the dark ones are the ones that are potentially best, but we weren't able to identify the actual best. But the light colored ones are the ones that we know are bad. In order to find the actual best scenario, we need to use another Simio add-in called select best using Kim Nelson method. So the KN method is one of the techniques under the general process of ranking and selection. And the way it works is that we sequentially increase the number of replications, and we continue this process until we're able to statistically find the best scenario. So let's go ahead and select the add-in and activate it, and Simio throws out this message that says, well, if you do this, your undo history will be gone and you cannot undo from this point on. So we say OK, and when we activate the KN add-in, we have a new set of properties for our experiment. Now we have the confidence interval that are used in the statistical tests, and we have this indifference zone that tells us the minimum practical difference that matters to us. So let's assume that we do not care about a difference of less than 0.02 in terms of the throughput. In other words, if I have a throughput of 59.1 and a throughput of 59.12, these two scenarios are considered practically the same, although the values are different, but from the practical point of view, these two have the same performance. We don't care about that slight difference between the performance of the two. And we can also set the replication limit. As I mentioned, what the KN method does, it sequentially increases the number of replications until we're able to find the best possible scenario. Sometimes we need to run a lot of replications and we don't want to do that. So we can set a maximum number of replications that we want the KN method to perform. So for this case, I'm going to set it to 50. And I'm going to now say run, and again the undo history will be cleared. It's okay, and we're going to let the KN method run, and as you can see, it increases the number of replications for the scenarios, and it has already decided with 11 replications that scenario 9 is not among the best set anymore, or is not a candidate to be the best solution. So it continues running, and it either stops when the best scenario is found or when we reach the replication limit of 50. So we have 43 replications of these four scenarios now, 45. Let's see when we stop. 49 and as you can see, we were not able to find the best scenario or the best parameter configuration using the KN method. So when I look at these histogram, the smart plots for the throughput, it turns out that I cannot select one of these scenarios as the best scenario based on 50 replications. An alternative approach to combine and separate entities is by using the batch and unbatch steps and using Simio processes. So in this model that we have here, we're going to use these two steps to perform batching and unbatching. So in our palletizer model, let's suppose that we have an infinite number of pallets available. Therefore, we don't care about the movement of pallets and the circulation of pallets anymore. We just care about the arrival of parts and their batching and their processing and when they leave the system. So as you can see in this model, I only have one source. Again, we don't care about the pallets anymore. We're assuming that we have an infinite number of pallets in the system. So I have my model entity 1, you can call it parts or whatever, and I have my source that generates entities according to the same uniform distribution we had before. And we have the same processing time distribution as well for our batches. But this time, we are going to batch the entities without using a combiner. In order to do this, what we need is, in our model elements, we need a batch logic. So in the model, under the elements, you see we have the batch logic item. So if we select this, you can create a new batch logic. And here, I'm going to set the batch quantity for this batch logic to pallet capacity -1. And the reason I do this is because this batch quantity indicates or represents the number of member parents. And since in this model I'm not using a pallet entity as the parent, but instead I'm using one of the parts itself as a parent entity, I need to set the batch size or the batch quantity to pallet capacity -1. So this -1 accounts for the fact that my parent is actually one of the parts that is in the batch. So if my pallet capacity is 4, then I need 3 members, and the 4th member will be the part that is considered as the parent for that batch. So if I go back to my model and go to my source, to the output node of my source, you will see that I have defined an add-on process at the entered at the output node of the source. And if we go to processes, here is the add-on process right here. What we're essentially doing here is that we track whether a batch is complete or not using a model state that we call track batch. So the track batch is initially set to 0. So if I go to my model definitions states, track batch is defaulted to 0. So when the first entity arrives, go through this decision right here that says if track batch is 0, which it is at the beginning of the run, then we take the true branch of the decide, we change the value of track batch to 1. And then we use the batch step to indicate that this first entity that arrived is going to be my parent entity for the first batch. And then I set the destination node for this parent entity to be the input at server 2, which is this node right here. And then, since the track batch value is non-zero, when the next entity arrives, I take the false branch of the decide, and this time this entity will be batched with my parent entity as a member entity. Once the batch is complete, I essentially set the track batch value back to 0, which indicates that the next arrival, or the part that arrives next, is going to be the first part of the next batch. And again, I'm going to use the batch step but this time I'm going to include this entity in my batch as the parent. So as you can see, we have two options for the category property. We have either parent or member that indicates whether you want to put this entity in the batch as the parent or as the member. Let's consider the case that my batch size is 4. So when I start the model, track batch is 0, my first entity is going to be my parent, and then the next 3 entities will be members, and when the batch is complete, I set the track batch value to 0, and then the 5th entity that arrives is going to take this, or the token associated with it is going to take this branch, the true branch of the decide, and the 5th entity will then become the parent of the second batch, and this process repeats. So now if I go back to my model and run the model, you will see that this first entity is going to be my parent, and then as soon as I have 4 entities, the first batch will move to the server, and it'll then be processed. So before I show you how the model runs, let's talk about this separation or split action also. So in my output node of the server, I have another add-on process at entered event. And if I go to this add-on process, you will see I'm using the unbatch step, which essentially works as a separator object. So I'm going to separate the parent from the members. So the parent is then transferred to the parent transfer node. So the parent entity is transferred to this node right here, the parent transfer node, and the members are transferred to the member transfer node that I have right here. So member transfer node and parent transfer node. It turns out that when you use the unbatch step, the parent is moved to the current node, so the parent will be at the current node. So in your transfer step, you transfer the parent from current node to the parent transfer node. However, your members will be unbatched and located in free space. So in your transfer for your members, you will have to have from free space to your member transfer node. So that was just a little trick in using the unbatch step. So from there, the parent and the members will be moved to the sink, and I have the same status label for my sink that tracks the number of parts that enter the sink object, or basically the number of parts that leave the system. So currently I have I don't have any pallets anymore, but since I have added this model to the same model that we had before, I still have this reference property here, but I have set my pallet capacity to 4. So I want the pallet size to be 4 in this model. So now when I run the model, I start with the first entity as the parent, and then the next 3 will be members of the first batch, and then my batch will be will move to the server, and once it's processed on the server, the parent is transferred to the parent transfer node, the members to the member transfer node, and they will all leave the system together. So when this first batch leaves the system, I expect to see a value of 4 for the number of parts that leave the system, which I get right here. And when you look at these two paths, it seems that we have two entities that leave the system. So let me set a breakpoint right here. The reason is the 3 members that I have in my batch, they just appear to be on top of each other, so we see them as one entity. But if I actually zoom in here, this is the input node of my sink, and run in step mode, you will see that I actually have 3 members on top of each other. So this is going to be the first entity, the second entity, third entity, and the fourth entity in that batch that leave the system through the sink. So again, in this video module, we showed 2 alternative ways of batching and unbatching using combiners and separators. Objects from the standard object library, and also we showed how we can do batching and unbatching using the batch and unbatch steps and using Simio processes. One last thing that I would like to mention is that the batch and unbatch steps do not appear under the common steps, so you will have to select all steps, and then you will see all different steps that you can use in your processes, and there you will find batch and unbatch